Hello, welcome back to NMI. Today I'm going to talk about the COSMAC Elf. Based on the CDP-1802 microprocessor from RCA, which I already mentioned here in the channel not long ago, this is one of the first open hardware single board computers ever. The COSMAC Elf was first introduced in an article published at the Popular Electronics magazine in August 1976. It was, even back then, a very low-cost single-board computer that was very easy to build and allowed almost anyone to get introduced to microprocessors and programming. The core of the COSMAC Elf is the CDP-1802, designed by RCA in 1974. Originally, it was a two-chip design, but later RCA revised the design and launched the CDP-1802 in 1975. The main characteristics of the CDP-1802 are full CMOS and static design, meaning it is a very low-power device, 16 16-bit general-purpose registers, one 8-bit accumulator, built-in DMA in and out, 64 kilobytes of memory address space, but it was particularly slow, and one instruction would take somewhere between 16 and 24 clock pulses. In spite of that, the COSMAC flew to space and even Jupiter. It was used in machine automation and other cool applications, and it's completing 50 years in 2025. And it is still in production, meaning it is the oldest microprocessor still in production in 2025. Now let's take a look at the architecture of this very interesting machine. Any of the 16 general-purpose registers can work as a program counter. That is mind-blowing. The current PC is set by a 4-bit register P. And yes, this is very unusual and allows some cool operations, as we will see later. Any of the 16 general-purpose registers can be assigned as a data pointer. This is set by the 4-bit X register. By default, P and X start as 0. There are special instructions for transferring data between D, the 8-bit accumulator, and the upper and lower part of a GPR. ALU-related operations always target register D. There are instructions to directly increment and decrement GPRs, but testing them requires the use of D. Incrementing and decrementing D can be achieved with ADI and SMI instructions using immediate data. There are conditional and unconditional branches as usual, but there are also skips. Personally, skipping instructions is something that I have only seen in some RISC architectures. There is no relative branch. In fact, there is no relative addressing. All branches are absolute, but short branches suffer from the limitation of page boundaries. There is no call instruction for calling a subroutine, but a subroutine call can be performed with some clever use of the instruction set. It supports DMA and interrupts. DMA operations are triggered by a DMA in or DMA out pins and use the register R0 as index. Interrupts can be enabled and disabled via the 1-bit IE register and use register R1 as the PC, meaning when an interrupt occurs, the program executes from the address stored in R1. Stack operations are supported via R2, and there are some instructions that can perform pop and push. And there is a special mode that allows DMA in to fill in the memory without requiring any bootstrapping ROM, and that is pretty cool. This is an important characteristic of the COSMAC Elf and allows the design of a simple computer without any kind of ROM, PROM, or EPROM. Just consider that other SBCs in the late 70s, based on the 8080, 8085, Z80, and 6502, required at least one ROM, PROM, or EEPROM with some sort of bootstrapping or monitor code. Now let's take a look at the COSMAC Elf design, both the original and my adaptation. Here we can see the original design of the COSMAC Elf as published in the Popular Electronics magazine in 1976. It used two 2101 RAM chips. Each one stores 256 by 4 bits. So together, these two RAM chips store 256 bytes of RAM. Because of that, there is no need to demultiplex the address bus. So this design was very simple in the sense that it didn't need to perform that kind of demultiplexing, right? Other characteristics of this design, we can see there are 8 switches that are used for inputting data into the system, into the program or data, right? And these switches are read through the 4016 ICs there. And the original design made use of those IC 6 and 7. Those are special HP displays that are capable of displaying hexadecimal numbers, right? So from 0 up to 9, and then A up to F. These displays are very hard to find. So this was one of my design decisions. I switched or swapped these displays for LEDs. The design also makes use of a crystal, and in my case, I'm not using a crystal. I'm using a crystal oscillator module. So I'm not. The original design made use of pins 39 and 1. For it has the CDP1802 has a built-in oscillator. All you have to add is an external crystal and loading capacitors. I decided to not do that, and I used an external crystal oscillator module. And the reason is that I want to be able to also feed external clock from another supply, and then we can maybe down the road change the clock frequency and even step instructions or run a program very slowly. So that is the reason I swapped the crystal. We can also see the design here connects an LED to the Q output. So we have a Q LED that reflects the state of the Q output. I didn't mention before, but there are special instructions to set and reset this Q output directly, right? And the CDP1802 also has 4 flag inputs. So basically it has one output that can be controlled by software directly, and 4 inputs that can be read directly by software. These inputs are EF1, 2, 3, and 4. EF4 is used here for reading the input switch, which is not shown here. Let me show you the next diagram. So here is the diagram that shows the other controls, right? We have a run switch, we have a load switch, an input switch, and the memory protect switch. On my design, I changed it a little bit how this all works. I mean, I didn't change the logic, I just changed these switches here, especially the input switch. They have 2 different contacts, right? So when you press it, when it's released, it makes contact on one side, and when you press, it makes contact on the other. I didn't want to use this kind of switch. I didn't even have one here, so I changed my design. One cool thing about this design is that it makes use of wired OR gates, right? So we can see here that D3 and D4, they make a wired OR gate. So we can take the load input here, R and 2, and those are tied together with this pull down resistor, and they become N2 or load, right? So if you have a signal coming from here or from here, This is a wired OR. There's another wired OR here that connects NOT load and SC1 to the reset line of this flip-flop. And the idea here is that you can set the flip-flop using the input switch, and then it's reset by SC1. So when SC1 is one of the two outputs that can be used to detect which mode the CDP is currently, or the COSMAC is currently in terms of instruction execution state. So SC1 goes to 1 when the DMA cycle is performed. So basically the circuit, you press the switch, you pulse the clock, and you send a DMA in. When the DMA is acknowledged, it resets the flip-flop, right? So this is a very clever design. Memory protection is very cool because it just prevents the memory write signal from reaching the pin on the memory that is gonna enable the writes. So basically, when you connect or you tie memory protect to the on state, you are forcing the memory to in an always read mode, and this is very useful because we can use the DMA to show, you know, the data that is stored in RAM, and that is we're gonna see that in a few minutes. Now let me show you my adaptation of the COSMAC design and some of the features that I added. Okay, so here we have my version of the COSMAC Elf. This is the schematics, right? The input switches are here, but I replaced that 4016, the CD 4016, the two CD 4016, I replaced with one 245 here, HCT 245, right? As I mentioned before, I also replaced the display, the two HP displays, with these 8 LEDs, and I am using this 74 HCT 574 latch to store the data that we want to show on the LEDs. Well, I didn't really show you, but the arrangement here with the logic gates is kind of the same, but I made some modifications of my own. So the LED latch here signal comes from mostly the same combination that we have there. The main difference here is that on the keyboard read function, I have a keyboard disable input that can be used by an external source. The main difference on my design is that I am making use of the full 16-bit address bus. So we have this latching the upper half of the address bus. It's another HCT 574, and we are using larger memories, larger SRAMs. So there are two options. One is a 2K SRAM, the 6116, and there is also the option of a 32K 62C256, right? So this is another modification that I added. I have this inverter gate here on A15, and the purpose here is that later on it is possible to switch by enabling this GP4. You can switch the RAM. Initially the RAM is assigned to the lower half of the address space from 0 up to 7FFF, right? But if you want, you can move the SRAM onboard to the upper half by just connecting this or soldering this bridge, and then that would allow an external memory to live in the lower half, right? But I'm not doing that right now. The design is placing the RAM at the start of the memory space. These pull-ups are also the same ones in the original design. I also added, as I mentioned before, a clock oscillator module here, and we have a clock disable, an external signal that can set this flip-flop, and then the clock here, the clock line is going to be tied to 1, and you can use an external circuit to input clock here, right? The switches that I used are slightly different, so I changed a little bit the design. I had to add some debouncing because I'm not relying on the natural debouncing that comes from the use of the original input switches. This is giving me a little bit of trouble, but it's mostly working. Maybe if you have any other suggestion, I'm open to any suggestions. This is working, but I think it could be better. The wired OR circuits that I mentioned before, they're still here, right? The arrangement here is basically the same. The only difference is that I'm not using the CD4050 that was used in the original design. I'm only using the inverters, the 4049 and the 4013 and the 4023, right? Which is this, it's I think three input NAND gates. What else? Yeah, and I have a USB mini connector for providing power to my COSMAC Elf. And yeah, I think that's it. Now, the next, oh yeah, I forgot, almost forgot. I added these two connectors here. So they are on the sides of the board, and this allows an external daughter or mother board to be connected to the COSMAC Elf, and it basically has access to all the signals that are required. So down the road, I'm planning on maybe adding another board that can, input data automatically into the COSMAC, maybe reading from an SD card. Also planning on adding some sort of display. Well, I don't know yet, but this is one of the reasons why I need support, and I encourage you to support me using my Patreon. But yeah, so this is it. This is the design of my COSMAC Elf. And yeah, another thing that I didn't mention, I decided to go with SMTs. So everything here is mostly SMTs except the 1802, obviously, and the crystal. The crystal oscillator is also a through hole device, and the switches, but everything else is SMT just because I find it's easier to handle. Yeah, so that's it. Now I want to take you, and we're going to start programming the COSMAC and taking a look at the cool stuff that it can do. So the first program is really simple. It's only 4 bytes. We have an REQ instruction, the rec, that is going to reset the Q, or turn the LED off. Then we have another instruction, sec, that sets Q to 1. And then we have a short branch to 0 that is going to make the program go back to address 0 here and start all over again, right? Each instruction here takes 2 cycles. And now let's take a look at how we input that into the COSMAC Elf. So this is my first version of the COSMAC Elf. I designed it using KiCad, and I made a couple mistakes as usual. The first one was that as you can see here, I am using I designed the COSMAC using mostly SMT devices, just because they are easier to find, in my opinion. So they're all modern parts. To be honest, a cool thing about this design is that everything here is brand new, right? Including the COSMAC. I was very fortunate to get 2 samples of new COSMACs from Renesas. But one of the mistakes that I made was that when I picked the package for these ICs here, and I think this is the HC574, I did not pay attention
and I ended up selecting a package with 0.5 pitch, which is very, very small, as you can see here, right? I wanted to pick a TSSOP with 0.65 pitch, but I ended up selecting the wrong parts. And I only realized that when I got the boards. And again, I was a little bit lucky that I managed to find these chips on Mouser. So I bought the same IC, but in this packaging that it's much smaller, and then I could assemble this board. And then I realized the other mistakes that I did. The major one was that, or is that, the switches are all inverted, right? That is, yeah, I didn't again pay attention, and the switches are reversed. So the off position is like this on when they're the handle is upwards, and this is the enabled position or the on position, right? So that is not what I wanted to do, but this is fortunately easy to, or not so hard to overcome. And then the other mistake that I did was that I redesigned some parts of the input circuitry, because I didn't want to use the same kind of switches that they used on the original project, especially the push button here. So I ended up designing a different circuit for the inputs here, but I made a mistake on the circuit and I had to work around it here. So this is why there is this resistor, right? But the good news is everything after these minor fixes I'm gonna demonstrate to you, the COSMAC Elf is working, this board, and I'm happy with it. And then after that I designed this other board that fixes all the issues, and it's also smaller, right, as you can see. But we're not going to talk about the newer board. First, I'm going to demonstrate that the older or the previous board is working. I have a USB connector here. This is just for power. There's no circuitry, like no converter from USB to serial or anything like that. So we can power the board. Is it connected? Yeah. Everything is off. Now I can switch, for instance, bit 1 here, and I can enable load. And if I press N, we are inputting a bit 1 or binary 1 into the COSMAC. What else? We can just play with this, and we can oh, it's the opposite. Feed up 2, then a 4, then an 8, then a 16, 32, 64, 128, right? And now we switch load off, and I'm going to enable memory protection here, this switch, and I switch back. Now the processor is in reset. If I enable again load and press in, we should be able now to see the contents of the RAM. So we see the one that I inputted before, the FA, then the other thing that what is this, FD, and then the like 2, 4, 8, 16, 32, 64, 128, right? And if we move ahead, now we are gonna see information here. This is all the garbage that is stored in the RAM, in the SRAM. The SRAM is this guy here, and that's it, right? So this basically demonstrates that the COSMAC is working. Now I'm gonna input a very simple program that is gonna blink the LED. And this is gonna be the last demonstration that I'm gonna do on this board. The first byte is 7A. So 7A. We're gonna put load in position and press in 7A. Okay. Then we're gonna do 7B. So this is A and this is B. And then we're gonna do a 30. 30. And then we're gonna do 0, 0. And this is it, right? Now we can just review the program just to make sure that everything is there. 7A, 7B, 30, 0, 0. Good, it's okay. Now I'm gonna switch it to run, and we have an LED blinking. But it's blinking super fast, right? Because there's no delay. And it looks like it is always on. But I'm gonna show you that with the scope, we can see then the LED turning on and off, right? And then we're gonna also be able to measure the instruction timing, right? Okay, as you can see, we see on the screen now the time that the LED is on there. Oh, cursor 1 is 200 microseconds. Let me fix that. Okay, now we can see there that the time that the LED is off is 8 microseconds, and the time that the LED is on is 24 it's 24 less 8, so 16 microseconds, right? I think we could just make this measure positive width and negative width. So 8 microseconds for the negative, the low phase, and 16 microseconds for the high phase, right? Now let me show you something else. We can it is this way because I am having an instruction first to turn the LED off, then we turn the LED or the Q output on, and then after that Q going high, we have the branch, right? So in fact, the time that the LED is on is just that duration of that REQ instruction, the rec instruction that resets Q, and the time that LED is on is the sec instruction plus the branch, because the LED is on during the branch, right? Now, what we can do, if I stop the program, and we're gonna see that the scope is gonna, let me change the trigger to auto. Now you can see that if I run the program, we see the Q output, right? But if I stop the program, we don't have Q changing anymore, right? Now, I'm gonna protect the memory, and we can inspect. So the first instruction is 7A, and then we have a 7B. What I am gonna do now is reverse or swap these two instructions. So I'm gonna do a 7B first and then a 7A, and we're gonna see that the waveform there is gonna be the opposite, right? So I'm gonna have a 7. Let me remove this for now. We're gonna have a 7B, 7B first. So we're gonna reset. We are going to start with a 7B followed by a 7A, right? And then I'm going to protect the memory, and let's see, we should still have the 3. Okay, so we're going to reset everything. 7B, 7A. Yeah, I am gonna have to enter the jump or the branch again. So reset. 7B, 7A. Now I'm gonna unprotect and I'm gonna supply a 30. Oh, yeah. It's that always gets me because this is all active, right? So okay, I'm gonna try again. We have 7B, 7A. Now I'm gonna input 30. Oh, the memory is protected. Okay, yeah. So here we go again. 7B, 7A. Unprotect the memory. 30. Input. Oh, finally, right? And then now 00. Okay. Now we are gonna move load to reset, and we're gonna put the probe back there, and I'm gonna start the program and look at the waveform. Now the active time, the time the LED is on, is lower or smaller than the inactive or the time that the LED is off, right? So that's why, because we reversed the two instructions. So this is it for this board, right? I am not going to do anything else on this board because, as you just saw, it's very error prone. I had everything reversed here. I don't like, and I wanted a better design, and that's why I designed this other board, right? So here we have my newer version, right? PCB 1.1, and it's smaller if we compare the two. This is slightly smaller, and I also arranged the switches in a different position here, right? So we have run and load here and memory protection here. The LEDs and everything else is in the same position. Maybe if I redesign this board, and I probably will, I will move these two switches a little bit farther from these ones, just so that we have it very clear, the functions, because this is a different function, right? And I might just move the nibbles here, the 4 bits slightly further, so that you can distinguish the two different nibbles. But this board is fully working, and I'm going to demonstrate it to you right now. As I mentioned, this board fixes the issues that I found in the previous version. I'm using larger packaging here, right? This is the TSSOP that originally I wanted to use. So 2 TSSOPs here. The diodes are also larger, so easier to solder. And here I still have the 2 footprints, but on this board I am using a 32K RAM chip. But basically everything else is the same. I have a footprint here. A friend of mine, Stuart, asked me for like a larger switch, so I have a footprint here for a larger switch like this, right? So if you want, you can assemble this board with a larger switch, which for me is fine. But anyway, that you have options, right? This is going to be on my GitHub, so you can just replicate, and the Gerbers and everything you can order from, for instance, JLC PCB. I will probably sell them assembled on eBay or something, so stay tuned.
This is the last program I'm gonna show in this video. It's a rather complex one. This program basically outputs binary counting on the LEDs, but it also has a delay that is configurable in steps of 1 millisecond. So I think that is pretty cool, a pretty cool example of how you can code on COSMAC. The subroutine here takes a parameter, so we're gonna see how that happens. Basically, the program starts by setting the address of our counter. In this case, counter is here on position 030 hex, right? we're going to use register RF to point to our counter. We start by loading 30, immediate 30 into D, and then we put D into the lower part of RF. Then we load immediate 0 onto D and put that on the higher part of RF, and now RF has 0030 hex. This is how you load stuff on a 16-bit GPR. Here we take the value that is still 0 on D and store that in the memory pointed by RF. Now that basically sets counter to 0 here, right? This is another interesting instruction on COSMAC, sex. Sex basically sets X register. X is the data pointer, right? So we're basically stating here that the data pointer now is RF, right? We're going to use that later. We're going to see that out here makes use of that. The next step here, oh, and by the way, yeah, I color coded the instructions to make it easier to understand each block. So this next block here, we are setting the address of our delay subroutine. You can see that the entry point of delay is here, right? 0x1e. So we set R3 as the pointer to our subroutine. So the procedure is the same that we saw before. We load the lower part and the higher part, right? So 1e and 0 onto R3. This blue area here is our actual counter, right? The magic happens here with the out4 instruction. Out4 basically is going to output the data to the address, the IO address 4, right? So it's going to select on N1, N0, N1, and N2 binary 4, which is the address of the LEDs, and it outputs the value of the memory pointed by the data pointer, right? In this case, data pointer, we set it here to be RF. So this instruction is going to take the value pointed by RF, which is our counter, and it's going to output to the LEDs. As a side effect, it also increments the data pointer, right? And that is an undesired side effect in this case. So this is why I have to decrement RF here so that it points back to our counter. Then we load D with 1, and we add that 1 to our counter, right? The value is still on D now, but the counter now is incremented. And then finally, we store our counter into the memory position, pointed by RF. Now, our counter here is going to have count plus 1, right? Here on this block is where we call the subroutine. We're gonna get there, but before that I just want to show this last step of this block here of the counter, which is the branch to loop here. So it's branching. This is something that I have to do manually here because I don't have an assembler, right? So branching instruction opcode is this, but I need to set the absolute address of the target, which is, in this case, loop is 0e. So I have to manually write 0e here. So this is something that you need to pay attention when you're coding this way. Now back to here. This is where we call the subroutine. Our subroutine here is taking a parameter on register RE. So RE is going to have the number of milliseconds that we want to delay. In this case, I'm loading 32, which is 50 decimal, right? So we want a delay of 50 milliseconds. We call the subroutine by setting the PC. So this is what the SEP instruction does. We set our PC to be R3, which is now, which is this guy. It has the address of delay. So from this point, the program jumps to the delay entry point here. Here in the delay, we load the immediate 0xD6, which is 221 decimal, and this is the counter that is going to tell this loop here how many times we want to repeat. The loop basically adds 1 ADI, it adds the immediate 1 to D, right? And if uh, and if D is 0, we long skip this instruction. Long skip skips 2 bytes. Here we have a branch to delay. So basically the way it works is if D is not 0, we're not gonna skip, and then we come here and we branch to delay address 20, which is here, right? So we keep repeating this loop, adding 1 to D until D reaches 0. When it reaches 0, we long skip these 2 bytes here, and we come here. Here we decrement RE, which is the total number of milliseconds we want to delay. And these green instructions, this green block here, is how we compare 16 bits. In this case, we're just checking if they are 0, right? So if the lower part, so we get lower, we transfer RE.0 or the lower byte to D. And if it's not 0, we branch back to delay and perform another loop. If it's 0, we check the higher part of RE. And if it's not 0, we also go back to delay. And if both of them are 0, then that means that we reach the end of the delay and we branch back here to delay ret. Now, this is a trick that we do because you can't have just the return instruction here, right? You need to put the return instruction here on the top of the subroutine for a simple reason. This way, we branch back here, and this instruction, sap R0, is going to set the program counter to be R0, which is the default PC, and that is going to return the program to where it was before, right? But it also increments the current PC, which is R3. So R3 now is going to be pointing to the entry point of our subroutine, and this is what we want. If this sap was here, R3 would be wrong, right? When we return, we would return correctly to the caller, but the next time we call the subroutine using R3, R3 is pointing to the wrong place. So this is why we put the instruction on top of the program, so that on top of the subroutine, so that the register points to the right entry point all the time, right? And this is it. This is how it works. So the subroutine returns to the caller. The caller now is going to run the branch loop. The loop is going to repeat. We're going to load RE again with the 50 decimal, call the delay, and this is going to repeat. So basically, we're going to see the LED counting and incrementing every 50 milliseconds. I have here on the side some calculations that help understanding how much time the delay is taking. And okay, now let's input this program and see it working.
Now we're going to input this new program, and it's much longer, so it's a larger program. So we're going to put load, and we're going to start F8, then a 30, AF, AF, F8, F8, 00, BF, F, oops, 5F, EF, F8, 1E, 1E, A3, so these two, A3, F8, 00, B3, B3, 64, 6 4 2F F8 0 0. Oh, I made a mistake. This was supposed to be 0 1. Okay, I'm gonna have to come back here and fix F4 5F F8 32 3 2 A E F8 0 0. This time it is 0 0. BE D3. This is CD 3 D3 3 0 0 E D0 F8 DD FC 0 1 CE 3 0 2 0 2 E 8 E 3 A 1 E 9 E okay 3 A 1 E 3 0 and 1 D. Well, that was a long program. Okay, now we're gonna have to review, and I need to replace that byte that I made a mistake. So reset the CPU. When I reset the CPU, I only reset the internal registers, right? So the contents of the RAM is still the same. Oops, protect the memory. So we start with F8, right? Yeah, F8, then 30, AF, then F8, 00, BF, 5F, EF, F8, 1E, A3, F8, 00, so that's the correct one, B3, 64, 2F, F8. Now is the byte that I made the mistake. Now I'm gonna unprotect the memory, and we need to input 1 here. And now we protect the memory, and we should see now the next one is an F4, 5F, F8, 32, AE, F8, 00, BE, D3, 30, 0E, D0, F8, DD, FC, 01, CE, 30, 20, 2E, 8E, 3A, 1E, 9E, 3A, 1E, 30, 1D. Oh, fingers crossed. Or yeah, here, fingers crossed. I am gonna switch load off, and let's put it to run. And yes, it's working. See? Now we have the counter, but with a delay. So that shows that the code is working, right? And we just programmed the COSMAC. I find this is an amazing CPU. Very nice. I like this design. It's so simple, and yet you can do cool stuff, right? As I mentioned before, I have these expansion ports here. So my intent in the future is to design another board that is going to plug on the bottom here, right? It's going to sit on the bottom. This is going to be connected like this. And this board is going to have some more advanced electronics to allow you to feed programs from an SD card. So you can, from your computer, you're going to be able to write programs and load them on an SD card, and then select on a menu and run, force the COSMAC to run those programs. I think it's going to be cool. Maybe we can have more features, maybe video, maybe sound, I don't know. But that is a next phase of a project, and this is why I need you to, back me up. If you are not, and I think you don't, because I don't have any Patreon, so please consider becoming a Patreon. I need your support to move forward. Subscribe to my channel, leave a comment on this video, because if you find it cool, the COSMAC, what I'm doing here, please leave a comment, share this video, and like this video as well, right? And I guess that's it. I hope you really enjoyed this video. I did, for sure. As I mentioned, I love the COSMAC. I like this design. It's very simple yet very nice. And that's it. Thanks for watching, and see you next time. Bye.